In this video, we're going to talk about uncertainty in measurements and how that uncertainty is related to the equipment, the person using the equipment, and other factors. Our choice in equipment is usually based on the accuracy and precision of the equipment. Take, for example, a balance. You're going to use a balance to get the mass of a sample. You have choices. First choice, you could use an analytical balance. We use an analytical balance because it can measure the mass to 4 decimal places, meaning that the uncertainty is in the 4th decimal place. With a top-loading balance, the uncertainty in the mass is much larger, usually in the 2nd or 3rd decimal place. So if we care to know 4 decimal places in the mass, we're required to use an analytical balance. Top-loading balances are easier to use, but because of their design, are incapable of giving us nearly as high of a precision. So here's an example of equipment and their uncertainties. Burettes are another good example, though they add a level of difficulty. So if we take a typical burette, let's say we have our 10 milliliter mark and our 11 milliliter mark, there's going to be 10 little tick marks between the 10 milliliter and 11 milliliter mark, one of them corresponding, of course, to 10.4 milliliters, let's say. Now, many people might say that this means the uncertainty in the burette is plus or minus 0.1 milliliters, because after all, that is the smallest measurement listed on the piece of glassware. But a more skilled user might say, well, I can estimate whether it's exactly on the line, right here, exactly on the line, or maybe I can estimate whether it's halfway. Such a person would say, well, I could get to plus or minus 0.05 milliliters. And then there's others, and this is what I would consider to be the typical way of using a burette, who can not only estimate whether it's halfway, but there's a good deal of ability to measure whether it's more than halfway or less than halfway. And if that's the case, we could say that the burette is measured to 0.03 milliliters. Now, in both of these cases, what we see here is that there's an intrinsic uncertainty associated with the piece of equipment. In the case of the burette, however, we see that there's also the influence of the user themselves and how confident they feel they are in their measurement. The next scenario is a little different. Let's say we're trying to make a solution and we weigh out 0.5112 grams on an analytical balance. So you can say the uncertainty in this mass is plus or minus 0.001 grams. Truth be told, if it was done by difference, it's 0.000141 grams, and that's the subject of a different video on propagation of uncertainty. But this is the uncertainty in the mass as it was measured. But what we care about is the amount that actually dissolves. And what happens in the likely scenario that not all of it dissolves? Well, then we can't suddenly say that we know that we have 0.5112 grams. So now the question becomes, how much didn't dissolve? Well, 100% dissolved is the easiest scenario, right? 100%, we don't see any solid floating around in solution. I think we could tell the difference between 100% dissolving and 10%. So that's not even a question. But could you tell the difference between 100% dissolving and 50% dissolving? Well, so let's look at this way. Let's say we have our weighing paper and we have our solid on top of our weighing paper. Would you notice if half of it were still there? You could probably tell if it was half still there. Not only that, you could probably tell if there were only 25% left. Right? So imagine if you broke this up into 4 pieces. They don't have to be, in your mind, 4 even pieces. Could you tell the difference between 100% dissolving and 75% dissolving, where you said, well, 3 of the 4 pieces in your mind have dissolved, whereas the other ones haven't? You probably could. Could you tell the difference between 100% dissolving and 90% dissolving, meaning 10% left? You could, presumably. Some people can, some people can't. And it depends on a lot of different circumstances. But you there in the lab have just tried to dissolve 0.5 grams, and some of it dissolved and some of it didn't dissolve. So let's try to work a calculation where we see how we would work with this. So imagine we start with 0.5 grams, and we feel that 90% dissolved. If 90% dissolved, that means our uncertainty is around 10%. So our uncertainty is of 0.05 grams, meaning that we feel the maximum that could possibly have dissolved, right? If we make a number line here, the maximum that could possibly have dissolved is 0.5 grams. We feel strongly that the minimum that dissolved is 0.45 grams. Because we're assuming that we're saying that on the outside 10% didn't dissolve. If that's the case, we know that it's not 0.5, we know it's not 0.45, it's somewhere in the middle. So let's see, where's the middle? 0.475 grams. And the uncertainty that we have associated with this is plus or minus 0.025 grams. So we would report the amount that dissolved as 0.475 plus or minus 0.2025 grams, or to the correct number of places with these last digits hanging. And so this would be our estimate of how much dissolved. And if you felt that really it was only 80% that dissolved, you could do the same thing here, and you would end up with 0.45 plus or minus 0.05 grams. And you could prove that to yourselves. Hope you found this useful and that this will be helpful for making uncertainty estimates and measurements of uncertainty.